Hello everyone, and welcome to session number 22 of the Discrete Maths 2 course. And as I was mentioning last time around, this is the last session in which we cover something new. The last two sessions of the course will be just repetition, sort of covering material that we already examined in the previous course sessions, focusing on things that perhaps were harder to understand. And this will also give you some time to start already preparing for the exam, which is on April 13th. So first day of the exams in the afternoon, this is going to be your first exam, I believe. I don't think you're going to have another one in the morning, or at least I hope not. Which means you have no time whatsoever to forget the stuff that you've been working with. That's the ideal situation. Okay, as usual, before we cover the new stuff, let's warm up by doing some exercises, which will allow us to refresh our memory of things that we've already seen, and also to warm our neurons up so that we are ready to understand everything new that we are going to do afterwards. So suppose that I have the following situation. I have a die, this thing, or sort of this thing. And don't ask me whether these dots are placed in the right place. It really doesn't matter for the experiment. And I throw it 4 times. Four throws of the die. Okay, what I'm interested in is whether I get 5 or 6 or something else. So I'm happy if I get 5 or 6. And I'm not happy if I get 1, 2, 3, or 4. So now I ask you, if I throw my die 4 times, how likely it is, what is the probability that I'm happy exactly 3 times?
1 by 27.
Okay, one of your colleagues is saying 1 over 27.
Right, that's 3, or that's 3, but that still leaves the last. But it could be either, so no.
Okay, so he said no.
Times 2, 3.
Okay.
1 over 27 times 2 over 3.
The second guess seems to be 1 over 27 times 2 over 3, you said? Okay. So my question to you is this correct? And if so, why? But more importantly, before we start throwing numbers at each other, even though numbers don't hurt too much, but let's wonder about sort of how we can go about figuring this out. So the question is, what is the probability that I'm happy 3 times, exactly 3 times, if I throw my die 4 times? Now, what kind of experiment is this? What kind of trial is this? It's a Bernoulli trial. Why? Because, okay, I'm throwing a die, so there are 6 outcomes. Well, in a Bernoulli trial, you want to have 2 outcomes, which are typically called success or failure. This accounts for the smiley and the anti-smiley. So this is what we could call success, the green stuff, and this is what we would call failure, the red stuff here. Now, even though we're throwing a die, this is really a Bernoulli trial. Why? Because every die cast is independent for all of the die casts that we have done before. That's important for a Bernoulli trial. And moreover, we've designed the experiment so that the outcome is binary each time. Either I'm happy or I'm not. So since this is a Bernoulli trial, what we want to calculate is the probability of getting 3 successes out of 4 trials. And now, what is the formula for computing this probability? And of course, the people at home are sort of browsing through the book or any other visual memory that they might have to find the formula. Okay, so let me ask you, okay, you're throwing the die 4 times. What is the probability of success when you throw it once? Success means I got a 5 or a 6. So the probability of success is 1/3. Now we want 3 of those, and they're all independent. So we take this to the power 3, because it's 1/3 times 1/3 times 1/3. The 4th attempt is a failure. And the probability of failure is 2/3, because it's 1 minus whatever we had, and 4 out of 6. Okay, we only want 1 of those, so that's why we don't put any power. Well, it's to the power 1. That doesn't change anything. But now we need to account for the number of ways in which I can succeed out of 4 trials. I could succeed by taking success, success, failure, or failure, success, 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 or other possibilities. Now, how many ways do I have to place 3 successes out of 4 attempts? 4, choose 3. Okay? Now, even though I write parentheses in 2 different positions, note this is the notation for a binomial coefficient. It's a bit unfortunate that they use parentheses for that, but that's the traditional way to do that. Okay, so now we can calculate and see whether we actually get the result that was suggested by your colleague. Okay, so 4 choose 3 is what? It's 4 factorial divided by 3 factorial times 1 factorial. I'm just spelling this out even though 1 factorial is just 1. Times 1 over 3 to the power 3 and 2 over 3. Now, what is this thing? This is 4 factorial divided 3 factorial is 4. And then we have 2 to the 2 over 81. In fact, that's exactly what your colleague was suggesting here. That's this multiplying. This 2 over 81. So actually, the initial guess made by your colleague was the probability of getting 1 successful trial. But there are 4 of those. That's why we need to multiply by 4. So this is actually 8 over 81, which is sort of roughly 0.1, roughly 1/10. So the probability of getting 3 happy casts of the die out of 4 attempts, where happy means I get a 5 or a 6, is, well, not too big, not too big. It's 1 out of 10. Sorry? Okay, so 4 factorial, the question is here, 4 factorial, yeah, divided by 3 factorial times 1 factorial, but 1 factorial is 1. So 4 factorial divided 3 factorial is 4 times 3 factorial, because it's 4 times 3 times 2 times 1. That's why only the 4 remains. Okay, so this was just by way of reminding you that sometimes knowing the binomial distribution can help you solve exercises like this in a jiffy. You just need to use a formula, namely the formula for the binomial distribution. Okay, so far so good. Now let me ask you something. Actually, let Dr. X ask you something which is conceptually, I would say, more interesting. Now, here's something for you. Somebody gives you a coin, and you don't know whether it's unfair or whether it's fair. You have no idea. Just to pepper things up, all you know is that this coin is unfair. Say the probability of heads is slightly above a half, but it's not completely unfair. It's not 1. So there is a probability, 1 minus p, which is non-zero, that you actually get tail. Now, you're computer scientists, and you want to simulate the behavior of a fair coin using this unfair one. What do I mean? What I mean is that you need to come up with a simple protocol that uses this unfair coin, and you don't know what the probability with the unfairness of the coin is. You just know it's unfair. In fact, you don't really need to know even it's unfair for the protocol to work, but let's assume that. And you want to simulate a fair coin. In other words, you want to use this coin so that you can decide in a fair way, sort of you want to get, using this unfair coin, the behavior of a fair coin. Something that half of the time gives heads and half of the time gives tails. Now, the reason why there is a picture of von Neumann here is that there is actually a very, very simple protocol that John von Neumann devised. Now, in case you don't know who John von Neumann is, you should, because he's amongst being one of the most brilliant mathematicians of the previous millennium. He was also one of the fathers of computer science. He was one of the guys who actually built the first computer. In fact, today we talk about the von Neumann architecture. That's this von Neumann. It's one of the fathers of game theory, which Google uses all the time to place ads on our pages with great success and make loads of money out of it. That's why they can afford to sponsor the Turing Award with $1 million now. Okay, so let's get back to my question. How could you simulate a fair coin using the unfair one that I gave you? So now I really sort of can feel the warmth of the neurons getting heated up in the lecture room.
Yeah, so you have no idea what P is.
You have no idea what P is. It doesn't really matter. That's one of the beauties of the thing. You have no idea. But it doesn't matter. Let me give you a hint. Toss the coin, the unfair coin, at least twice. So let me give you some scratch pad. Okay, so here's your coin. Let's make it a euro coin, so that we can be very popular with some politicians. The probability of head is P. The probability of tail is, okay, my 1 minus P. And you know that P is between a half and 1, with the extremes excluded. In fact, it could even be a half. It doesn't really matter. So suppose I toss this coin twice and I get head, tail. What is the probability of this event? It has the same probability as tail head, which is P times 1 minus P. So these two events here have the same probability. Okay? So why don't we call this one head and we call this one tail? But now you might say, okay, well, there are two more outcomes. Head, head, and tail, tail. Well, what if I get one of those two? What would you do? You just restart, absolutely. I mean, we are computer scientists. We know about iteration or recursion, so we just restart. Tough luck, I just restart. Now, sooner or later, I'm going to get either a head tail or tail head, because the probability that I always keep getting tail tail or head head becomes zero very, very quickly. Okay? So if somebody gives you a coin and you don't know whether it's fair or unfair, it doesn't matter. You're computer scientists. So what do? You just apply a little protocol for simulating the behavior of a fair coin, even though the original coin was not fair. You just toss the coin twice. If you get head tail, you call it a head. If you get tail head, you call it a tail. And if you got anything else, repeat. Isn't it cool? It's certainly not complicated. At least once von Neumann showed it to us. It's the kind of thing that any of you could have figured out with a little bit of thought. I myself needed to read it, but that's another matter. You're smarter. But anyway, sort of a simple protocol that works no matter what P is. But again, you're a computer scientist. As computer scientist, you might want to ask yourself, well, I mean, on average, how often do I need to flip the coin in order to get a head or a tail? And you know, this is related to what we started covering last time and what we're going to cover today, namely the expectation of a random variable. In this case, the random variable counts the number of flips before we actually get a fair head or a fair tail. And the formula, which we are not going to derive, but I'll just give it to you, is that the average number of flips that you need to make is 1 over P times 1 over P. That's the average number of flips. So in particular, for instance, if P, say, is 2/3, then this will be 1 over 2/3 times 1/3, which is 9 over 2. 4.5 flips. That's what you need to do on average. And the more unbiased, so the more biased the coin is, the more flips you need. Because the higher the probability that you get head, the more chances, the more trials, the more flips you will need in order to get the tail. So this makes a lot of sense. Absolutely. So your colleague is saying if P is a half, then you need 4 flips on average.
Is that 4 flips overall or 4 like.
So 2 trials, 2 repetitions of the experiment.
Yeah, okay.
So it's 4 flips of the coin, actual flips of the coin, which corresponds to repeating the experiment twice. But note, if somebody gives you a coin, well, of course, if the coin is fair to begin with, you don't need to repeat anything. But if somebody gives you a coin, you have no idea whether it's fair or not. In fact, most likely it isn't fair, because even though the coins are mass-produced, it's not God-given that they are actually completely balanced. In fact, they are not. Some people actually calculated the probability of heads and tails by doing lots of experiments, and it's not really a half. There is a slight bias somewhere. And it might even depend on which coin you pick. But this experiment always works, regardless of whatever funny coin you get. It doesn't work if the coin has 2 heads, because in that case, you never get a tail. But let's assume that that's not the kind of thing that happens. In any event, it's something that you could easily check by looking at the coin. Okay, so this was too cool. I mean, I needed to show it to you. Also because it's a simple algorithm that allows you to turn an unfair coin into a fair one. Okay, so this thing about computing averages of the values of random variables is really what expectation is all about. So you might recall that last time around, your colleague here sitting on my left sort of told us what the average value of a die cast was. And he said 3.5 is the magic number. Inspired by De La Soul. 3 is the magic number. Well, for us, it's 3.5, at least for this specific experiment. And it's not magic. It's actually the average. It's the expectation, the mean value of a random variable that assigns to each die cast its value. Now, why is that? Well, each one, if the die is fair, and we are assuming that it is fair, each one of the numbers from 1 to 6 can appear with probability 1/6. So the average number is 1/6 of the time we get 1, plus 1/6 of the time we get 2, plus, yeah, he's too quick, you see, sort of, I'm a slow guy. I want to show it, and also I like to write. But yes, you're absolutely right. This is 1/6 of the sum of all the numbers between 1 and 6. And now, of course, you know how to calculate the sum of all the numbers between 1 and 6. There is a nice formula that I think you've seen in all kinds of sources. Today will be the carried version, which tells you how to do that without actually doing the calculation. It's, well, there is a 2 below here. It's 6 times 7 in this case, okay? The sum of all the numbers between 1 and n, no matter what n is n times n plus 1 divided by 2. And what is this? The 6's above and below the fraction cancel each other out. So we have 7/2, which happens to be the magic number 3.5, which is not magic. It's just that mentioning the word magic makes it more interesting somehow. Okay, that's the weighted average. This is nothing but the expectation of the random variable that assigns to each die cast its value. Okay, so for instance, if somebody asks you, before we actually give the definition, let's do another example. Suppose instead I'm interested in the random variable that gives me the number of heads that I get in 2 throws of a fair coin. Okay, so this is a random variable that goes from a sample space. Okay, random variables are nothing but functions from a sample space to the collection of real numbers. Now, what is the sample space here? The sample space consists of all, I'm throwing a coin twice, so it's all the possible combinations of heads and tails of length 2. Cool. So S will be head, head, tail, tail, head, tail, tail, head. And now, since the random variable is supposed to assign the number of heads to each one of the possible outcomes, so we will have that x of HH is 2 and blah, blah, blah. Okay, so what is the average number of heads that I get? Well, each one of these outcomes, since the coin is fair, occurs with probability 1/4. So it's with what probability 1/4, I get 2 heads. With probability 1/4, I get no head. And with probability 1/2, which corresponds to these 2 scenarios, I get a 1. I get 1 head. Because it's 1/4 plus 1/4, so it's 1/2. Okay, so what is this? Okay, so this is 1. This thing is 1/2. This thing is 1/2. So I get a 1. Which makes a lot of sense. Why? Because if the probability of getting a head is 1/2, on average, I expect that if I toss my coin twice, on average, I will get 1 head. So half of the times I get a head. Since I toss it twice, half of the times is 1 time. Once. And actually, this makes perfect sense because this is really the frequentist approach to probability. Why do we assign the probability of head and of tail to be 1/2 when the coin is fair? Well, because if you keep flipping, repeating the experiment, flip the coin a hell of a lot of times, you will see that roughly half of the time you get a head and roughly half of the time you get a tail. That's where the probability comes from. In fact, some coins are less fair than others, but that's life, isn't it? Sort of, you know, sort of life is a bitch, and then we know what happens. Okay, sorry, this has got nothing to do with probability. Unfortunately, it's got to do with certainty, but you never know. Cryogenesis is making lots of steps. So if you've got enough money, then you can join some Russian tycoon in Austin Powers in a freezing department. Anyway, let's forget about this. So what is the definition of this expectation of this average that we've been using? This is the question that you're all burning to see answered. I hope you're not burning too much, but that's another matter. Okay, so we have a random variable, x, over a sample space, S. What is the expectation of x? Well, that's the formula, and that's the one that we've been using already without giving the formula. You take the weighted sum and weighted by the probability of the actual outcomes of the probability of getting outcome S times the value of the outcome. And you sum it for all the possible outcomes. If the set of possible outcomes is finite, this sum is always defined. But if the set of possible outcomes is countably infinite, there are chances that this sum might not actually give you a value. It might be infinite in value. And in fact, it might even be minus infinite, or it might fluctuate because you know, the value of a random variable could be a negative real number. Fortunately, all of the cases that you will see, this sum will be, well, nearly all of the cases, this sum will be finite. Or it will be easy to calculate. Okay, so let's put this formula to work. Let's start by looking at a slight variation of the example that we just did. Now I'm interested in the random variable, number of heads, but not in 2 tosses of a fair coin, but in 3. 3 tosses of a fair coin. Okay, so what is the expected number of heads in 3 tosses of a fair coin? Let's calculate. Okay, now my random variable, x, has a sample space which corresponds to strings of length 3 over the alphabet head-tail. And what does this return? If I take a string of length 3, let's call it A1, A2, A3, then this will be the number of H's in A1, A2, A3. Okay, so what is the expected value of this variable? Now, first of all, before we actually do the calculations, which are particularly boring, what would your estimate be? Sorry? 1.5, one of your colleagues said. I would expect this to be 1.5. Now, let's see. What would your reasoning be? Remember, before we calculated the expected number of heads in 2 coin tosses, and this was 1. Now you toss 1 more, and the probability of getting a head is 1/2. So if you sum 1 with 1/2, you get 1.5. So this sounds sort of reasonable. Well, in fact, it sounds very reasonable. So let's see whether the formula actually gives us our guess. If the formula doesn't give us our guess, there are 2 possibilities. Either we made the calculations wrong or our guess was wrong. And since this is not a mind-boggling calculation that we can check with the calculator, if the formula doesn't give the 1.5, then our guess was wrong. Okay, so let's see. Now, how many possible outcomes do I have? They're all equally likely. So what is the probability of any single? It's 1/8. All of them have probability 1/8. Now, what we need to figure out is how many ways do we have to get different values? What are the possible different values? So how many ways do I actually have to get 3 heads? There's only one. Head. Plus, okay, let me keep putting 1/8. Let's forget about the 0 outcome because there's only one and it's tail. So how many ways do I actually have to get 1 head? Well, the 1 head could occur in any of the 3 positions in the string. So there are 3. Each one of them has probability 1/8. So I have a 3/8. Plus, How many ways do I have to get 2 heads, exactly 2 heads? Okay, so I have 3 possibilities here, and I'm doing 3 choose 2. And these are the 2 places where I want to put my heads. So it's 3 factorial over 2 factorial. It's 3, isn't it? So the question is, shouldn't the first one be 1/8 times 1, not times 3? Well, you see, this is we're calculating the value of the random variable. And the value is 3 heads in that specific case. So with probability 1/8, the value of the random variable, the number of heads, is 3. Here, I'm calculating the probability, sort of the expected value, so the probability that the expected value corresponding to the situations in which I have 1 head. So with probability 1/head, I get sort of, so consider the possible outcomes: head, tail, 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 head, tail, and tail, tail, head. Each one of them gives me outcome 1 with probability 1/8, and I sum them all, I get 3/8. The last one should be just a second. The last one should be, you have 2 heads. There are 2 possible, absolutely. That's 6. That's 6/8. So what we get is 12/8, which is actually 1.5. So the guess was okay. So in other words, what we just did was the following. We summed for all the possible bit strings, because the sequences of head tails are nothing but bit strings of length 3, the number of heads, sort of x of s, that's the number of s of heads in the bit string, times the probability of that bit string. And in longhand form, that would be sort of, you would have 8 arguments in the summation, and for each one you get this. So you would have 1/8 times 3. That's when you get the outcome head, 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 plus 1/8 times 0. That's when you have tail, 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 plus 1/8 times 1. That's when you get head, tail, tail. And you continue this way with all the possibilities. And this is what you get at the end. Any problem with this? Okay. So you want to see all the calculations? Okay, so the problem is the understanding. Okay, sort of, look, you're summing over all the possible 6 strings of heads and tails of length 3. And for each one of the strings, you take the value of the random variable for that string, which is the number of heads, times the probability of seeing that outcome. So when you're looking at head, 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 the probability of seeing the outcome is 1/8, and the number of heads that you see is 3. And you do this for each one of the possible outcomes. So for instance, if the possible outcome is head, tail, tail, then its probability of occurring is still 1/8. And the number of heads that you've seen is 1. Okay? So, for instance, if I instead looked at the string head, tail, head, the summand that would correspond to this string would be what? The probability of seeing this string, which is 1/8, times 2, which is the number of heads. Yes, question. The question is, do you do this for all the possible outcomes? The answer is yes. So the more outcomes you have, the more in trouble you are in the calculations. However, what we are going to see after the break is that, in fact, there are two important properties of expectation that actually simplify calculations enormously. So, in fact, for random variables like this one, we don't need to look at all the possible outcomes. We can simplify the calculations enormously. Because suppose instead of tossing the coin 3 times, I would toss it 1,000 times. And I asked you, what is the average number of heads that you get? Now, the collection of all possible outcomes now assigns 2 to the power 1,000, and you don't want to actually expand that sum. And you don't need to.
2 to the power 1,000.
Yeah, you don't want to know how many they are. Yeah, 2 to the power 1,000. That's big. Okay, so after the break, we are going to see how these calculations can be simplified no ends.